So, recall an abstract algebraic variety x comma kx, where x is a set and kx is a finitely limited level. Reduced K algebra, and such that there is a bijection between x and the maximal ideal of kx. So, right, and then you defined a map kx. If you have two such abstract variety, you define map x from y to ky. So, one is f and f hash. Such that f hash of g at x equal to g of f of x makes sense. Similarly, g of fx makes sense for all g this f okay, I should write one time before writing this, where f is a map from x to y and f hash is a K algebra map from ky to kx. K algebra homomorphism, such that f hash of g at x equal to g of f of x for all g in ky and x in x. Right? This is how we define. And now you define isomorphism between two abstract varieties, that if you have g hash such that g composition f is identity, g hash composition f hash is identity, and g hash set, and if composition g is identity, f hash composition g hash. So, isomorphism is suitably defined. Okay. And so of course, if you start with a algebraic set or algebraic variety V, which is in K, say A in K, then you can associate V comma KV, which is a abstract variety. So, point is that converse also holds, that if you start with the abstract variety V comma KV, then you can associate a variety in some AN. So, this is the point. So, every algebraic set gives rise to an abstract variety but the converse also holds. Converse is also true. And so, converse also holds, and not only that, if you have a morphism like he was asking, if you have a morphism from V to W, converse also true. So I leave it as exercise, assignment problem. Okay. Use the generators. So generators, because it's a finitely generated algebra, you will be able to embed V into some affine space. And only thing you have to say that there are enough functions which can distinguish points. If you have 2 points, because you have to prove something is embedding. So if you have 2 points, you will get an embedding that under this map, this is a different, they go to different points. So embedding, so that is only one thing which you have to check. And not only that, if you have a map from V to W, a affine algebraic set, suppose V is in A in K, and this is in A M K, then of course this will give a map from K W to K V naturally, because a morphism is defined in this way, right. Converse also holds. If you have a K algebra homomorphism, but now the point is that if you have a map from KW to KV, so then you have a map from, so KW, so you have a map from V to W. So converse also holds. So this way also you have a map. So I leave all this as exercise. These are all nice exercise. You can try your, just use the finitely generated algebra. Kx and ky are finitely generated algebra. You are right. Just like if you want to embed something V into An, you have to give n regular functions. And what are those n regular functions? They will be some kind of generators. Yeah. So you have to use that, and also K algebra homomorphism also you have to use at some point. So this will say that a theorem that this affine, or I denoted the algebraic sets by this category, and this K algebra category, where the objects are K algebra reduced, I should write it. So reduced, finitely generated algebras. This is a one-to-one correspondence, and this is the equivalence of categories. And so these two categories, you can think they are equivalent. I'm not going into what is equivalence of categories and all, but you can think that they are same. I mean, in some sense, to isomorphism. Okay, so this is the upshot of yesterday's lecture. So now we will now see, we defined algebraic set. Now we will define a topology on. See, without topology, you really cannot do anything in mathematics, right? So you have to define some topology on your algebraic set, and that is called Zariski topology. So like in differential geometry or anywhere, you see that whenever you do some topology, first you use the topology of some metric topology like Rn, Cn, and then you try to use that. You take the subspace and then use the subspace topology. It's exactly same way. So first, because algebraic sets are subset of the affine space, so first you give topology on the affine space. Once you give the topology on affine space, then that will induce a topology on a subset, closed subset of the X, so the affine space. So that's how you do. So this is topology on algebraic set. So this is known as this topology has some name. It is in terms of in the name of Zariski, Oscar Zariski. So, it is called Zariski topology. So, before that, first I should say something that see when if I take, suppose take the polynomial ring k x1 x2 xn, and if you take an ideal, see when we define algebraic set, we took some 0 set of some system of equation, but that system of equation you can take the ideal generated by that system of equation. So, 0 set of that ideal is same as 0 set of that system of equation. So, because working with ideal sometimes is easy, because you can do some commutative algebra. So, I will do back and forth, sometime I will take generators, sometime I will take ideals. So, because they are all fine and there are only finitely many generators, because we are in Noetherian situation. Okay. So, first of all, we know by Hilbert-Nullstellensatz that if you take an ideal A, then V of A and V of radical A, they are same, right. 0 set of a radical ideal and 0 set of an ideal, these are same, right. So now if I say that I define in AN the closed sets, I am giving a topology say on AN, the closed sets are of the form V of A. Since V of A is same as V of radius, so these are V of radical ideals, because radical ideal class is smaller. So, it is enough to work with a radical ideal. I mean. Okay. So, now so there is a 1-to-1 correspondence between radical ideals. So, if I define my closed sets of AN are 0 set of an ideal, so then radical ideals in k x1 x2 xn and closed subsets of A and K, there is a 1-to-1 correspondence, right. What is a 1-to-1 correspondence? So, if you start with some closed subset here x, so you send it to the ideal defining x, Ix, set of all functions, set of all polynomials which vanishes on x. And now, if I take something in some ideal A, you send it to 0 set of A. And this is a 1-to-1 correspondence. So, now the proposition, assume algebraic close, because I will use Hilbert-Nullstellensatz everywhere. Let us not bother about non-algebraically closed field, because things are, you have to be a little bit careful and you need scheme theory to understand those maps and all. So, let's assume everything is nice. I mean, nice means algebraically close. Proposition. Oh, sorry. The sets, the closed sets is radical ideal forms a topology or gives a topology. Topology on affine space. Yeah. So, to say that what you have to prove? To say something, some collection of subsets which you consider as closed subsets. So, we need to, so first of all, to give it away, first we have to say that phi and the whole space it is there. Obviously, because phi is some v 0 set of 1. V is a notation, right? What notation I am, either V or Z, which notation I am using? V. Okay. Harshon uses Z. Yeah. So, and of course, A and K is 0 set of the 0 ideal. So, empty set and the whole topological, the A and they are part of it. Okay. So, now what you have to prove that if you take a infinite intersection of closed sets, you have to prove this is a closed subset. So, this is a closed subset and of course, finite union. So, V of A union V of B. So, in intersection, what is the correct? It should be correct choice. If you make it smaller, so the ideal should be bigger. So, it should be V of summation AI, but summation AI and union AI they are same. 0 set of, where you think as the generators, everything is finitely generated. So, AIs are finitely, so there are finitely many elements. So, if you take so what is V of AI? So, suppose AI is generated by F1, F2, FR. Then what is VAI? This is the common zeros of F1, F2, FR. So, it is basically intersection of V of Fi, right. So, now you take some, sorry, it should be a, let's write. Right. So, now if you take finite, if you take a family, so then it will be like this, right. So, common zeros of F1, F2. So, and what is VA union VB? What it will be? It's product. It's like Fi Gj. If Gj's are the generator of B and Fi's are generator of A, then the union will be like if you take the union of two axes, for example. You take x axis and y axis. X axis is y equal to 0 and x axis is x equal x axis is y equal to 0 and y axis is x equal to 0. If you take union, it is nothing but xy equal to 0. Similarly, for if you have a multi-generator, also that is true. So, this will be V of AB. So, you need to check. I will leave it as exercise. Okay. This is just you will take it. Is not difficult to see, but you need to do it. Or at least once you do it, later you can forget. So, for example, if you take right. So, now consider now for example, if you take x equal to A1 the affine line. So, what are the closed subsets? So, these are any ideal is a principal ideal, right, in Kx. So, principal ideal means it is 0 set of some polynomial. I mean the 0 set of the principal ideal is 0 set of some polynomial. So, any polynomial you can write it some x minus A1 dot x minus an. So, then V of f will be some bunch of points. Now, I am using algebraically closed field. K is algebraically closed. You can write it as the linear factors and C is some constant, right. So, in A1K, so then what is the topology? So, closed sets are finite set of points. So, that means that in A1K, the affine line, the closed sets are finite set of points. Yeah. Yeah. So, now of course, okay. So, okay. So, okay. See, if we start with some ideal, suppose if A is an ideal in kx1 x2 xn, need not be radical ideal. Now, if you take the 0 set of that, and then if you take the ideal of this is radical of A, right? We have seen Hilbert no sensors. But now suppose suppose y is any subset of the affine space. Now, you can talk about the ideal of I of y. So, this is what is Iy? Iy is set of all functions f in k x1 x2 xn such that f of y equal to 0 for all y belongs to y, right. This is an ideal, because if I take two function f and g, f plus g also vanishes on y. F g also, if I take any element in k x1 x2, if I multiply with element of iy, then again it vanishes. So, it is an ideal. So, now you can talk about v of iy. So, this is a closed subset, but y is any subset. So, v of iy, of course, it will contain y. Yeah. So, y is by a priori is here, but this is a closed subset. But this is a canonical closed subset from y. So, what is a canonical closed subset of a subset of some topological space? Is a closure. So, that is the theorem. So, I will leave it as exercise. For any y in v of iy equal to y. So, this is closure of y. Closure in the sense of Zariski topology. Y in. So, take this as exercise, prove it. So, that means what you have to prove that so to show you have to show. So, this is what you have to show, that if I take any closed subset, this is closed, if it contains y, then you have to say that W contains V of iy. So, then this is true for any, so that means the V of closure of a subset is the intersection of all closed subset containing the subset. So, this is the hint. Okay. So, now as you see this example, that the union of axis. So, x axis union y axis, right. So, this is say x, this is y. This is nothing but V of x y, right, in affine plane. So, this you are writing as V of x union of V of y. But V of x or V of y, you cannot write further as V of union of two closed subsets. So, these are in some sense they are called irreducible component of x y equal to 0. For example, this curve like this is irreducible. This kind of curve you cannot write as union of two closed subsets. But this curve, this is also singular, this has a node point, here also you have a nodal point, but whenever you have some union of two things, if they are not disjoint, then the point is a point of singularity. I mean, you agree, right? I mean, at least one dimensional case. Such thing appears. So, one needs to define what is called irreducible closed subsets. Irreducibility. So this is nothing to do with algebraic variety. Suppose X is a topological space. This true for any topological space. You can make this definition. X is a topological space. And then X is called irreducible if you cannot write X as y1 union y2, where y1 and y2 are two proper closed subsets. y1, y2. For example, the union xy equal to 0, 0 set of that is not a irreducible topological space. Of course, it has a topology because A2 has a topology. So, now you induce a topology on the subset that under that Zariski, under that topology, this is not a irreducible. You can write it as a